So here is our setup. If I had a 0 over here, then this would be a just basic harmonic oscillator setup. But instead of 0, I'm putting this forcing frequency, this push and pull, and this forcing term. And the frequency, the angular frequency of the forcing term is omega. And my main question is, how does the response of the system, also known as the solution of the system, react to different choices of omega? So that's our question. And you might notice that this is a slightly different than what I had back there. I had divided by m here. But, you know, A was just like an amplitude that had units of force. Now I'm going to make it an amplitude that has units of acceleration. Doesn't really matter. So it's just some forcing amplitude. You know, if you scale everything by mass, then it's not going to drastically change our answer to these questions. So just to simplify things, I'm going to replace a over m by a. Okay, so to address this, let's solve in the way that we know how to solve. And just let's not be afraid of the unknown a and unknown omega. It's okay that these are unknown things. So here's the strategy. Same strategy that we learned about in the previous lecture. Solve homogeneous, get x1, x2, right? Then we get the general solution. So we want the general solution to the homogeneous. That's why we want two linearly independent ones. So these are linearly independent. Then solve non-homogeneous. Just one solution is what we want for that, and then add them. So let's start with number 1. That one basically we already did, right? So guess e to the lambda t, get lambda equals, how about I write the polynomial? We get lambda squared plus omega naught squared equals 0, because that's the homogeneous version, so I'm imagining that I have 0 here. Excuse me. And then I get lambda naught equals plus or minus square root negative omega naught squared, also known as plus or minus I omega naught. And this is complex, so I get a complex solution, which is e to the plus minus I. So let me just pick one. I only need one of them. Let's say plus I omega naught t, right? This is my solution. This is my e to the lambda t, with lambda being that. And then I can write it out in terms of the real and imaginary parts. So cosine omega naught t plus I sine omega naught t. And I just have this pure oscillation. And let's call this one x1. Let's call this one x2. Those are my two linearly independent solutions. Great, that was easy. Now for the less easy. Solve the non-homogeneous. Get just one solution. So let's let L be the thing that's happening to x on the left side. So what is happening to x is we're taking a double time derivative and then applying that to x, and then we're taking omega naught squared and multiplying that by x. So I'm choosing L so that L applied to x is the left-hand side of the differential equation. That's the idea when I'm describing L. Okay, now let's give this its own clean page. The differential equation, let me just copy this info over. So this is our L, this plus, this is omega squared here. And then we want an x such that this is true. This is our differential equation, is this, right? So what is the form of the forcing term, the right-hand side? It's a sine omega t. So what kinds of things do I plug in to get sine omega t type stuff? Well, if I plug in sine omega t, that would give me sine omega t type stuff, right? If I plug in cosine omega t, that would also. So if you want to think about this in terms of the guessing table, the form of my source function is something times the sine of omega t, where my omega is literally the variable omega, so I've left it as an unknown. And so the trial form for a particular solution, a good guess would be something times the sine of omega t plus something times cosine omega t. But don't be confused by this a here, since I'm using a as part of my forcing term. So if you look at what I'm doing here, I have put a here that playing the role of what they're calling alpha. So don't get confused by this. A good guess is a linear combination of sine omega t and cosine omega t. So let's try that. Okay, so a good guess is a linear combination. Let's call it b sine omega t plus c cosine omega t. And I want to choose, so b and c are here are my undetermined coefficients. A is not an undetermined coefficient. Don't get confused about that. A is the forcing amplitude. So that's like a parameter that is built into the differential equation, right? It's fixed beforehand, just like omega and omega naught, and back here, the mass and k. Those were all fixed into the differential equation. So A is fixed into the differential equation. B and C are undetermined coefficients. I want this to be A sine omega t. What is it actually? Actually, it's LB, L sine omega t. L is linear, so it distributes like this, right? Plus C, L cosine omega t. So some people were asking why I look at L sine omega t, L cosine omega t individually versus just computing this all at once. I'm just basically breaking apart the calculation into little bits so I can see which parts I need. It just feels better for me to do it this way. So let me take L sine omega t and calculate that. Or put another way, this feels more organic to me. It makes sense to me that if I want a sine omega t type thing to come out, then I could try sine omega t to put in and then see what I get. And then what I will get will probably involve cosines. And then I'll be like, well, how do I cancel away the cosine? And then probably I'll use cosine omega t. So let's just see. L sine omega t is, so this apply to sine omega t. So take two derivatives. Two derivatives applied to sine is going to be negative sine. But each time I take a derivative, an omega pops out due to the chain rule. So I'll get omega squared negative sine omega t. Okay, plus now omega naught squared times sine omega t, right? Because when you apply L to something, it applies two time derivatives, and it also adds multiplying the thing by omega naught squared. Okay, interesting. So omega naught squared minus omega squared, all times the sine of omega t. That actually seems like enough, right? That seems like enough. What's the point of even putting in the cosine guess? So I could put it in, right? Cosine omega t, and I'm just going to get stuff involving yeah, let me just do it to demonstrate. But from here, it looks like this is sufficient, right? Like, how about I just stick an A or a B here, and then see what B has to be to get this to come out to be what I want. But let me just do the full thing. So L applied to cosine omega t is going to be double derivative of cosine is negative cosine, but again, an omega comes out. Each time I take a derivative, I'm taking two derivatives, so two omegas pop out, and I get omega squared here. Cosine omega t, and then plus omega naught squared cosine omega t. So that's omega naught squared minus omega squared cosine omega t. So now I know what this is. It's b times this, which is this, plus c times this, which is this. So let me get this kind of scratch work out of the way and just write down what I got. Here I got b times, and it was sine, I already forgot what it was. Excuse me. Omega naught squared minus omega squared sine omega t. Okay. Plus here c, and then this one was the same thing but with a cosine. All right. So this will give us two equations with the two unknowns b and c, right? Sine omega t and cosine omega t are linearly independent. So the overall equation is this equals this, right? What I want it to be. So which parts do I match up? The b omega naught squared minus omega squared, I match up with the a, so those should be equal. And then I think of this as, let me use a different color, I think of this as plus 0 cosine omega t, right? And then the 0 I match up with this part. So I have these two equations. A equals b omega naught squared minus omega squared, and 0 equals c omega naught squared minus omega squared. And my goal is to solve for b and c. So want to solve for b and c. Remember why? Because if I solve for b and c, then this will be a particular solution to the original, this differential equation. And that is step 2, is to get just one particular solution. Okay, so I want to solve this. So do you see how to solve it? C is 0, right? If 0 equals this, then C will have to be 0. Okay, well, unless this is 0. Okay, but certainly C equals 0 will be a way to solve it. Well, then what's B? So here's what we want. I think B equals a over this is a solution. I think this is a solution. But do you see the problem? What if I just divided by 0? What if omega equals omega naught? So what if the denominator is 0? That happens if and only if omega equals omega naught. That would be a problem. So then this wouldn't work. If omega equals omega naught, then here my equations are a equals 0 and 0 equals 0, right? Those would be my equations. And unless a happens to be 0, which is it's not, it's the forcing amplitude, I want to imagine a situation where the right-hand side is not 0. If a is not 0, then there's no way to solve this system, right? If omega equaled omega naught. So then what would happen? Well, in that situation, I would be in that caveat situation that we were talking about, right? Where basically omega is omega naught. So what I have on the right-hand side is one of the fundamental solutions. It's what I called x2 over here. Then I have to apply the idea in the caveat. And that will lead to a very different looking situation. So we have to split those two cases and deal with them separately. So let's allow this and throw in an assumption. So let me put assumptions in red. So assume now that omega is different from omega naught. So the driving frequency, the frequency with which you are going in and wiggling, is actually different from the natural frequency that it would normally want to wiggle at. Then, under this assumption, the denominator here is not 0, and this works. So then the rest of our solution would be, c equals 0. That would solve it. So really we only need, we never needed this term. We only needed this term here, and we got this times sine omega t. So we got our particular solution. Let me go back to this page. So after the assumption, assuming omega is different from omega naught, we got a particular solution, which is A over, what was it? A over omega naught squared minus omega squared times, which one was it? Sorry. Times sine omega t. Okay, and now we add them and we have our general solution. So let's add. So general solution to the thing as a whole is C1 cosine omega naught t plus C2 sine omega naught t. That's the x1 and the x2, our fundamental solutions, plus our particular solution, A over omega naught squared minus omega squared sine omega t. Nice. Now, depending on your initial conditions, that's what will determine, your initial conditions are going to determine what this part is. And, it's going to determine, it's going to determine what C1 and C2 are. The other stuff is all sort of fixed into the problem, right? Omega naught is part of the problem, part of the setup. A is part of the setup. Omega is part of the setup. So only C1 and C2 here are tied to the initial conditions. So now we have kind of answered this question, but I think we can answer it a little bit more clearly. How does the response of the system react to different choices of omega? Well, this is how. This is how the solution depends on omega. You see omegas showing up in different places here. But we can get more insight out of this than just, blah, here's a formula. How about we try some particular initial conditions so we can plot some things? So how about x of 0 equals 0? That's a nice one. Just to kill off some parts. I actually don't really care too much about the initial conditions. I'm more interested in how the thing is going to react to the wiggling. So let's just start it from equilibrium. And let's make it as simple as possible. Let's start it from equilibrium and at rest, and then just start wiggling it from there and see what happens. So this, I see when I plug in time 0 into here, I get this dies, and I get C1 times 1. So this tells me C1 is 0. And here I have to take the derivative to think about this one. So let me just do that quickly. So first I need to think about x prime of t. That's C1 omega naught cosine omega naught t. I failed to take the derivative actually. Minus sine omega naught t plus C2 omega naught cosine omega naught t. Oh yeah, but didn't I already decide that C1 is 0, so I don't care about this. Okay. So I'm just trying to take the derivative of this. And I already know C1 is 0, so this term is already dead. And I've got C2 omega naught cosine omega naught t, that's the derivative there. And then A omega over omega naught squared minus omega squared, and then this is cosine omega t. And then that means x prime of 0 is, so that's C2 omega naught, just C2 omega naught. And then this one is just the coefficient in front, because cosine of 0 is 1. And this is, let's see, I'm setting this equal to 0. That tells me C2 omega naught equals negative A omega over this. Then let me divide both sides by omega naught. write this fraction out there. Okay, so then finally let me write the solution that satisfies those initial conditions. So if I have these initial conditions, then here's my particular solution. So C1 is dead, C2 is that, so we've got negative A over that sine omega naught t, and then this thing. All right, interesting. And I can pull out this overall factor. That's kind of what I wanted to show you. That's why I'm doing this. So I want to pull out that overall factor, and I get a difference of sines of different frequencies. So that could be kind of funky looking. The kind of oscillation you get there could be funky looking, but overall it's multiplied by this factor, which unsurprisingly scales with A, if A is the forcing amplitude. So yeah, it makes sense that if you if you double how hard you're pushing and pulling, then the response and the displacement doubles. That's pretty intuitive that might happen. But interesting also is the denominator. Think about what happens as you change omega, which you can think of as how fast you're wiggling. By fast, I mean frequently. With what frequency are you driving the system? If omega is very close to omega naught, then the denominator becomes very small, right? Then the fraction becomes very large, so you get a very high amplitude response. There's the wine glass breaking when the opera singer or whatever hits just the right note. That's omega being very close to omega naught. So this denominator is small and the response amplitude is very, very large. On the other hand, if omega is not so close to omega naught, then the denominator is large and the fraction is small. So if you wiggle a system that has a restoring force with a wiggling frequency that is very close to or equal to its natural frequency, the way it would wiggle if you just left it on its own without touching it, then you can get, in this way, the highest amplitude response, the most dramatic response. All right, now I want to plot the solution for fun. And don't worry, I have not forgotten that we made this big assumption here. We're going to look at what happens when you don't make that assumption. But right now, let's plot this solution. So for the sake of plotting, I'm going to fix the natural frequency of the system to be 1. And I'm going to fix the driving amplitude to be A to be 1. So this is 1, and that's 1. And I just want to look at how the system responds to changes in omega, the driving frequency. So if omega is close to 1, then I expect very high amplitude response. Okay, so I've typed in here the function. It looks like I forgot a space there. This is the function, and I'm thinking how far to run time. How about we run time for a few, 2 periods of with respect to the natural frequency. So I think 1 period would be 2 pi over omega naught. So let me run 2 periods, so 4 pi over omega naught. Okay, what's going on here is I haven't said what omega is. My whole point here was to manipulate. Although I suspect that error is about something else. But let's manipulate omega here. And let's vary it from, so when omega is close to 1, we expect some crazy stuff to happen. Let's vary it between 1/2 and 1.5, so that in the middle is the weird stuff. And, yes, I haven't evaluated this cell. There we go. There we go. Okay. So here's my omega bar. So I'm getting some kind of oscillation. Now, okay, this is kind of annoying that the vertical axis changes size. So let me keep the vertical axis sort of fixed. Let's make it run from -5 to 5 and see how that looks. Okay, so here's omega. Let me show you the values at 1/2. And then as I move the bar, it will change from 1/2 to 1.5. So let's look. By the way, what you're seeing here is T and X, the displacement. So this is how it responds, how the mass on the spring responds or whatever. And what I'm varying here is the driving frequency. Okay, so as the driving frequency gets close to 1, you see the amplitude of the response grow, and then it starts shrinking again as I shrink the driving frequency. What if I make it exactly equal 1? Can I? Let me type in 1. So a little bit less than 1 is okay, a little bit more than 1 is okay, but at 1, aha, you see? It's a division by 0 error. So it cannot even really show me what's going on at omega equals 1. By the way, I think maybe we can learn something from running this for longer than 2 periods. How about 4 periods? Or even more. Yeah, that looks pretty interesting. 3 periods of the natural. So yeah, you see, it's pretty interesting, right? And look what happens as omega gets close to 1. Things get pretty crazy. Let me make the plot range even larger so you can see just how crazy things get. How about -10 to 10? So the reason this doesn't just look sinusoidal, it looks kind of weird, is that I'm combining 2 sines that have different frequencies. This is what tends to happen. Yeah, you see? At omega equals 1, you get kind of very dramatic, it just wiggles harder and harder and harder and harder. And hopefully that there's some intuition there to what's going on, is that you're sort of the driving force is always in sync with how the system is responding. When the driving frequency equals the natural frequency, you can have the driving force kind of accelerating the mass along when the mass is already on its way in one direction, and then accelerating along in the other direction when it's anyway on its way in the other direction. Whereas when there's a mismatch, like this or something, this is like, a person who's on a swing, and then instead of you pushing them every time they're trying to accelerate forward anyway, you push them at random times. So even when they're coming back against you, you push against them and slow them down. So here the driving force sometimes takes energy away from the system, and sometimes it adds energy into the system. That's a way to think about it. Whereas here they're in sync, and the driving force is always adding energy to the system. So what happens at omega equals 1? Let's look at that in the next video. Before that, I want you to notice something interesting. So let me run this for much longer, so you see many periods. So I want you to see for certain values of omega the kind of thing that you see. You see kind of a wave within a wave, right? So for certain choices of omega, especially choices of omega that are kind of close to omega naught, so not too far away, kind of close to omega naught, like these choices and these choices, omega a little bit more than omega naught or a little bit less, you see what looks like a wave within a wave, right? It's kind of going boop, one wave, but if you look inside, it's going these little waves inside the wave. So one way to think about this is if you if you use some trig identities to rewrite this difference of signs, you can write it as a kind of one sine function multiplied by a sinusoidal amplitude. That's one way to think about it. Just like with some of our earlier, I think in the previous lecture, we saw some functions that were like sine of omega t and then times some exponential. Like, I don't know, maybe something like sine of 2t times e to the minus 3t times 5 or something. Then we think of this exponential decay as the amplitude. And then when we plot it, we're like, oh yeah, the amplitude is decaying, but it's also a sinusoidal function. So you get this decaying oscillations behavior, right? So there we were thinking about the sinusoidal function as being multiplied by an amplitude that's changing in time, and it's decaying exponentially. So there's this like envelope that it's forced into, and you get decaying oscillations. Well, here, this is like the amplitude of one wave is waving along another wave. So this phenomenon here, this is called a beat frequency. The frequency of the large waves, when you have kind of a wave within a wave like this. This is pretty cool on its own, and it's worth looking at, just since we're here. And you will look at it yourself in this homework problem, homework problem 4. So you will use a certain trig identity. It'll be suggested to you. The differential equation is a little different. There's a cosine here rather than sine. But basically you'll use a trig identity and see if you can write your solution out. So initially you'll write a certain solution with some initial conditions. Then you'll try to write your solution out using the trig identity as a certain sign times and then something times the sine of something. So it's like this is like the amplitude is another thing that's waving. Okay, so that's fun. This video kind of ran a little long, but there's still another part that should be part of it. So I'll put that in the next video, and that's we assumed that omega is not equal to omega naught. What if omega actually equals omega naught? Here we're seeing what happens when omega is very close to omega naught. Is you get craziness, right? The amplitude just keeps growing and growing and growing. But if you look here, like it grows and grows and grows, and it eventually comes back. That's that beat frequency thing I'm talking about. So it beats. So it eventually comes back. What happens if it's actually equal to 1? Well, what you should get from the picture, what's being suggested is that it would just keep on growing. Like this would just keep, the amplitude would just keep growing forever. So let's see if we can get that out of the math, out of our methodology for calculating particular solutions to these non-homogeneous systems. So I will do that in the next video.